to the course, everybody. Today I'm going to start by talking about the winner's curse, and then we'll talk about markets, which is also another way for interactions on the network. But first, again, I want to ask for a moment of silence for the people in Ukraine who are fighting for their freedom from ours. Okay, so let me go to... Remember we saw last time, the second price auction is really the best one. Bidding your true value is a dominant strategy. That means it's by far the easiest, the best, and you don't have to know about anybody else. Okay? We proved that. We also saw first price auction, which is not so easy. You have to, it's not so easy to figure out. You have to bid less than your true value. But how much less? Actually, it's hard to figure out because you have to know the other bidders. Knowledge of the other bidders. So it's much more complicated than second price. This one is less used, okay? So there's two opposing forces there. This is actually much harder to analyze. Okay, and then there's all pay. But now let me first start today by talking about the winner's curse. So this is a very famous property of auctions. La malédiction du gagnant, the winner's curse. And this is a special, it's an auction when the bidders, they want to resell the object. So if I want to buy an object, but I don't want to keep it for me, I want to sell it again, like I'm in a store, or maybe I buy an oil field and I want to sell the oil. So that means the real value for the object is what I sell it for. So the object has all the bidders have the same common value. They all have the same value, not different values, because they want to resell. And they all want to resell the object. It could be like an antique store. They buy the antique, but not for them. They want to resell it. But the common value is not really known. It's hard to know really what the value is. So each bidder kind of estimates the common value. So we're going to assume that each bidder has VI, so this is not the bidder's true value, but it's what they guess is the common value. So the antique store owner is guessing that the statue is worth 1,000 euros, and maybe another store owner guesses it's worth 1,500 euros, okay? So they're kind of guessing. And in the model, we assume that there's some real true value, V, and each bidder's guess VI, and so there's some error here. So this XI is like a random number with mean 0. Maybe they guess too high to guess too low. But there is this common value that each bidder guesses. That's the difference. So that makes a big difference. Okay? That leads to something called the winner's curse. Okay? Assume that an item with common value is sold in a second price sealed bid auction. Is it still the dominant strategy to bid VI like before? It's not anymore. And here's why. So assume there's very many bidders, okay? And they all have their guess, V1, V2, V3. So the one who wins is the one who guesses the highest. But probably that's going to be more than the real value. The winner probably overestimates. So maybe the statue is really worth 800. But the bidder who guessed 1,500 is going to win the bid. Way, he's the winner. But he will not be able to sell the statue for 1,500. It's only worth 800. Okay? So the winner will lose money when he tries to resell the object. This is a famous property of this kind of auction. If you buy something, if you just want to resell it, you have to be very careful that you don't bid too high. So because if all the guesses are like random numbers, then the highest random number is going to win, right? And probably it's going to overestimate. But even the second place bid, second price auction, will probably also be overestimating. So the winner's going to lose money. This is called the winner's curse. And it's a real thing that happens a lot. Okay? It's a general property of auctions when bidders want to resell the item. And an example is in the petroleum industry. So you have an oil field. Okay, you have a piece of land, and there's oil underground, you think. And all the oil companies are bidding. So the real value is how much oil there is, really. But nobody really knows exactly, they're guessing. But the one who guesses highest is going to win, but maybe there's not that much oil there, okay? Or baseball contracts to baseball players or soccer players in Europe, football players. So the value is the future performance of the player. How good is Lionel Messi or Ronaldo going to perform in the future? Maybe he's going to turn into a lazy bum once you pay him 10 million, okay? Who knows? But the highest bidder is going to get the player. Well, he better hope the player is going to perform, okay? Or else he loses. Okay? So some more examples of this. So an oil field, let's say it has a true value of $10 million. That is the amount of oil that's underground. The true, real value is how much oil there is. And the oil companies are guessing, and they guess from 5 million to 20 million. Well, the company who gets 20 million is going to get the oil field, okay? And if it's a second price auction, they will pay what the second guy guessed, but maybe the second guy guessed 15 million, so they still lose 5 million, okay? They better hope the second price is less than 10 million. But nobody knows really the real value until you start pumping the oil, huh? So it's a guess, okay? Okay, other examples, many examples. Spectral auction, like radio frequency. Companies are doing this frequency for like mobile telephones and things. The spectrum is actually owned by the government, and it's sold, the use rights are sold to companies, and billions of euros can be paid for that spectrum, okay? Well, the company buying the spectrum is going to use it for mobile phones, so they're not using it themselves. They better hope they have a lot of clients. Or IPOs. This is what's called initial public offering. A company sells shares, des actions. A privately held company, so a company that has no shares but owned by some people, they want to increase the capital. They become public companies, so they sell shares. How much do the shares cost? Well, they do an auction because they want the highest. Okay, so the person buying the shares, it's not the share that has value, it's the fact that there's a company doing stuff that has value. So if I pay a lot for the share, it means I hope the company will do very well. Okay? So I'm not buying share because I like this nice piece of paper, okay? And I think it's worth a lot. No, I buy the share because the company has value. So again, you have winner's curse. Or pay-per-click advertising, okay? So this also has kind of winner's curse. It depends on how much value the people put on that click. So the company guesses that tuberculosis is worth something. How much is it really worth? Don't know. The company doesn't care. The company is going to resell, and someone else is going to use the tuberculosis stuff. Or the supermarkets. This is also a really big thing. Retail, supermarkets. So I go to Aldi and I buy orange juice. So the Aldi has bought a huge lot of orange juice from some orange juice company. And Aldi makes an auction. Which company does the cheapest in this case, huh? So the one who bids the lowest, but then there's a hurricane and the price of oranges goes up. Oof, so I'm stuck. I still have to give Aldi the orange juice at low price, okay? So yeah. So winner's curse is a real thing. So how do you take it into account? You have to take it into account. That's not easy. So a rational bidder has to take it into account. So it's not only VI, but you also have to make sure that if you win, that you don't actually lose money. Okay? Winning has to be better than losing. Okay? So how do you do that? Well, that's not easy. You have to make some estimates of the error. You have to know something about the other bidders. But the basic idea is that the value of the bid will be less. Because high bid becomes risky if I bid too high. Even with second price, I will bid less. Okay? And in second price, it goes less. But in first price, it'll be even more going down. Okay? Because I'm paying the first price. So in both of these formats, the bid will go down. Because I don't want to be the loser when I win. Okay? So this is complicated. And it depends on knowledge. The knowledge you have of the other bidders, of the estimate, of the variance. It's complicated, and companies try to figure it out. Okay, so that's the common value auction. So you see this in this notion, the bid has to go down. So let me make a summary. I actually made a better summary now. If you look at auctions. So the most important one is sealed bid, second price. Bidding your true value is dominant. So this is the best one, and the bidding is very easy, and everyone is very happy, and you don't have to guess. Now there's also first price auctions where you have to bid a little bit less than your true value. So why is that? You tell me, okay? I told this last week, so you should be able to give some explanation. And the all pay, it's even lower than that. So why is that? You have to explain it. And also the common values, this leads to winner's curse. So the winner's curse is only with common values. Huh? These don't have a winner's curse. Huh? So here you have winner's curse. So a second price auction, you have to lower your bid. But if it's a first price, it even goes down even more. Huh? Because you're paying your price and not the second. Yeah. Okay. That's right. A question? No? Okay. So that's what we saw in auctions. And now that we go talk about markets. Okay. So let me take a step back and explain a little bit the course. So far we saw two things, really, before, graphs and game theory. Yeah? So the graphs is the social networks with human beings. They become friends, so strong or weak, or enemies, negative links. And the graphs will evolve. They will converge to triadic closure, also to structural balance. So graphs like to be balanced and closed. Okay? And then we saw game theory. This is social networks, but now we interact. It's not just the human beings being friends, but they actually interact, compete with each other. They have games, they have strategies. And then we saw individual rationality for selfish. We saw dominant strategies, Nash equilibria. We also saw what happens if we want the whole society to be benefited. We saw Pareto optimality, social optimality. We saw traffic networks and auctions with game theory. Okay, so we saw that. Now today we're going to extend that to markets. So markets also we're going to study it with game theory. Markets is different, is something economic. It's like auction, but now you have many buyers and many sellers, okay? And you have prices. It's not just bidding, but prices will fluctuate, they go up and down. Okay, sometimes you have traders, stores are in the middle. Sometimes you have to bargain. So there's more things happening. Okay, so that's what we're going to see in the next 3 weeks and next 3 courses. And after that, we'll see some applications, the structure of the web, how you do search, things that happen on the network, like information cascades, network, what's called network effects, power laws, small world phenomena. So after that, we're kind of going to look what things that happen in the network. Okay? But today we're going to start looking at matching markets, and first matching markets. So this is chapter 10. Okay? So let me introduce this. So network, we're looking at networks, and we have participants. And before, we saw auctions, okay? We have bidders, so buyers and a seller, or many sellers and one buyer. And markets is another kind of interaction like that. A market is kind of interaction between many participants, and they exchange goods. So some of them want to offer goods, and some of them want to need the goods, they want to get the goods. And it could be for money, or it's called barter, troc in French, where you're just exchanging services. And the way markets work is that there's some mechanism that coordinates. You have millions of buyers, millions of sellers. How do they know what to do? So again, there's this problem like with the auctions. How much are things worth? Okay? And the way that markets are coordinated is the prices. So the price is a coordination mechanism. Okay? Prices are used to regulate. Prices go up, there's less buyers. Prices go down, there's more buyers, but maybe less sellers. So the prices are like a controlling mechanism. Okay? And the economics is a kind of game theory. So we're going to keep talking about game theory stuff like payoffs and strategies and things. And there's many kind of markets, of course. There's real markets where you go on the street and you buy fruit, but there's business markets, but also many, many markets on the internet. And even kind of invisible. If I want to buy a book on the internet, I will not buy a book right away on Amazon. I prefer not to buy Amazon because Jeff Bezos is rich enough. I don't want to make him richer, okay? I look at other websites first. Maybe I look at eBay, where people are selling their books. And so it's a market for buying and selling books. And Amazon will regulate their prices, okay? And the other sites too. And the buyers and the sellers will do things, okay? And then there's also financial markets. Okay, so there's many kinds of markets. So we're going to study markets. Okay. Markets are complicated things. There's many things there. So it's huge. You can do a whole degree, you can spend your whole life studying markets. So I just want to give you the main things. So we're going to study markets, okay? There's a word too much there. In this lecture, we're going to introduce idealized markets. Just a second, let me fix the light. Okay, I don't like bugs in my slides. Okay, this is better. So the idea is markets are complicated. So we're going to make some kind of a simplified, ideal market. And it'll be very simple. It'll be like bipartite graph. And we'll study that. And we'll see how the prices the prices control everything, okay? And then once we get some understanding of the idealized thing, then we will see how it works in the real world. And the point is that the intuitions that we get from the idealized will still be good. So the idealized is chosen very carefully, so it really helps understand, okay? And we're going to study 3 steps. First, we're going to study supply equals demand. L'offre égale la demande. This is called matching. Matching is when there's exactly one buyer for each seller. And it's determined by the prices. Prices are the way that it regulates things. Okay? And on the internet too. That's what we're going to study today. Next time we'll study intermediaries. Maybe the buyers don't see the sellers, but there's a trader in the middle, like a store, a supermarket. So the trader has some power and some influence. And on the internet you see a lot. If I buy something from AliExpress, maybe you've done it, it costs 10 euros. But if I see the same thing on Amazon, maybe it costs 50 euros. Well, Amazon is an intermediary, okay? And they're getting something. So we'll study that. And we're also studying bargaining. Bargaining depends on your position. Where are you in the network? Are you on the edge? Is the buyer only talking to you? Or can the buyer talk to 2 sellers? If the buyer can talk to 2 sellers, the sellers have less power. But if I only have 1 seller, then it's like monopoly. Okay, so we're going to talk about that too. But today we'll talk about matching markets. Okay? But before I get into it, let me first explain a little bit again how the course is organized, the whole course. Because it's kind of a new and kind of abstract, so it's important to understand how we do it. We study real-world interactions, people on networks. And the general approach we do in the whole course is we make an ideal formal model, and then we'll apply it to the real world. So we make an ideal model, formalize it, study the properties, maybe prove theorems, and then we will adapt that to the real world. Structural balance, and then we saw how World War I appears from the friends and enemies. Okay? So we saw many examples already. In social affiliation networks, we saw how friendships are made. So the formal model is the model with this focus idea, like the clubs or whatever. So that's kind of formalizing friendships. There's also structural balance, so friends and enemies. Okay. We also saw games with rational players, rational meaning selfish. They do what they think is good for them. This is doing competition but cooperation. Each player wants to maximize, but they're actually working together. And then we saw benefits to society, the Pareto and social optimality, and today we're going to see matching markets. Okay? So the main idea is prices. So keep in your head the notion of price. Okay? Prices is the concept that connects everything today, even though you might see many things. Okay? So we start with a simple kind of market. This is called a bipartite matching market. So remember, bipartite graph has a bunch of nodes on one side, a bunch of nodes on the other side, and connections. A matching market, a market that has each buyer is matched to the item. Sometimes it's perfect. You have perfect matching. So this is bijection, where all the buyers have one item and all the items find the buyer. Perfect matchings are really the goal because they make everybody happy. Okay? So that's what we're going to look at. And in a real-world market, real-world markets will never be perfect. Okay? But they're always converging. They're always going toward being perfect. Okay? prices are the mechanism, the main. So here I say one decentralized mechanism, but it's actually the main mechanism for making the markets perfect is prices. So prices will usually converge so that the matchings are perfect. And when that happens, we have supply equals demand, okay? So that's kind of the goal. This is a natural goal. All the markets will automatically converge to that. If you let each player do their selfish things, then it will go to that. So that's why people love markets. It's this wonderful, decentralized, very stable convergent mechanism. Okay? Of course, in the real world, it's not always so simple, but it actually works pretty well. And we'll just look at matching markets. So each participant has different preferences. So maybe they buy a house. One of the people thinks the house is worth $1 million. The other one thinks the house is worth 500,000. So they have different preferences. And prices, again, will cause decentralized allocation. And also, it can lead to socially optimal. So it's actually very good for the whole society, okay, the market. Okay, so let's first I'll start with a very simple example. And then we go to something more realistic. Okay? So the simple example is called the Bipartite matching market. So here's a very simple example. You have 5 students and 5 rooms. So they want to rent a room or a studio or something. So a college assigning dormitory rooms to students. Each room accepts 1 student, and each student lists possible acceptable rooms. So for example, Vikram likes rooms 1, 2, and 3, Wendy likes room 1, Shin likes room 2, Yoram likes room 2, 3, 4, 5, and Zoe likes room 5. Okay? So each person has preferences. Okay? 5 students and 5 rooms. Very simple. So this is a bipartite market with the buyers and the items separate. Okay? Notice in parentheses here, I say not all matching markets are like this. Sometimes the markets don't have buyers and sellers. So the example I give here is DVD swapping. This is in the old days when people still used DVDs. Okay? Maybe you remember that. It was a long time ago. Very primitive things. DVDs. But customers have DVDs they want that they can share and they can exchange. So the customer is both the buyer and the seller, and there's no money. Okay? So this is not bipartite. But we will focus on bipartite because this is the usual thing. Okay? Okay, so you see that, right? So we can make a perfect matching here. Okay? We want to assign each student to a room they will be happy with. All the different students go to different rooms. This is called a perfect matching. So here we have a perfect matching. Okay? Equal number of nodes on each side. A perfect matching. Each node is connected by an edge. And it's one-to-one bijection. So no 2 left nodes are assigned to the same right nodes. Each person has a different room. And each room goes to a different person. That's a perfect matching. That's right. Interesting, right? That's reasonable, huh? Okay. Okay. Very good. But it might be that the graph does not have a perfect matching. So here, for example, so this is an example. This is a little bit different from the previous one. I removed Vikram's link to room 3. Yeah? So here's a variation. This one does not have a perfect matching. Okay? And how do you show that? We can prove it very easily. Very clean way. If you look at these 3 students, Vikram, Wendy, and Shin, all 3 of them together, they only are selecting 2 rooms. Okay, so the set S is going to a set N of S, which is the rooms. the neighbor set, huh? And the cardinality of n of s is less than the cardinality of s. That means you can't put 3 students in 2 rooms, okay? Each room is only for 1 student. Okay, so this is called a constricted set. Constricted means you can show that the corresponding items there's less of them. If the cardinality of n of s is less than cardinality of s, it's constricted. So showing a constricted set is a proof that there is no perfect matching. So this is a pain, okay? In this case, we can't make everybody happy, okay? And in economics, you can have this too, but in economics you have a thing that helps. You have the prices. So if this occurs in economics, we will change the prices so we don't have this, okay? So this is something that is where people are not happy, okay? So you can show, so this is a theorem. If a bipartite graph with equal numbers of nodes on the left and the right has no perfect matching, so there's no way of making everybody happy, then it must contain a constricted set. Okay, so this is important. We're going to use it later. So here, this graph has no perfect matching, and here's a constricted set. So you can show that's general. There's always a constricted set in there. Okay? And I'm not going to give you the proof of this here, but it's actually in the book if you want to look at it. So how do you prove it? So here's kind of the idea of the proof. Consider a maximum matching. You put as many nodes as you can in the matching, okay? And it works. And now we try to add one more node to it. And that normally will not work, okay? Because it's maximum, and there's no perfect matching. So you try to add one more node, it doesn't work. And adding that node actually shows you a constricted set, okay? Adding that node is going to show you with the other nodes, you are building actually constricted set. Okay, so that's kind of the intuition. Okay, so that's a pain, right? You can't, if you want to assign students to rooms, sometimes it doesn't work. But in economics, you have a solution. And the solution in economics is prices. So that the prices actually solves this problem. And with prices, you will always have perfect matching. Okay? So we extend this example now with prices. So these are like prices. They're called valuation, but it's because it's the value that each person assigns to the room. Okay? So for example, Shin thinks room 1 is worth 12, but room 2 is only worth 2, and room 3 is worth 4. For Yoram, room 1 is worth 8, room 2 is worth 7, room 3 is worth 6. For Zoe, it's 7, 5, and 2. Okay? Now, even though we don't have perfect matching, we can at least do like best possible, highest quality. Okay? So for example, if Shin goes to room 1, that gives 12. If Yoram goes to room 3, that gives 6. And if Zoe goes to room 2, that gives 5. So it's 12 plus 6 plus 5. The quality is 23. And you can try to find a matching with the best quality. Okay? Okay, this one is actually optimal. Okay, this example. So as exercise for you, to see that you understand it, prove it's optimal. Show me there's no higher one. Okay? And also, the original room assignment problem, this one, is actually a special case of the price model. Okay? If you choose prices in the right way. Okay? So show me how that works. So this is the first step. Now we have these bipartite graphs. And we introduce this notion of this is a valuation. I mean, because it's what the room is worth to me. It's still I'm not paying anything. Yeah? So far I'm not paying. Price is what you pay, but this is what it's worth. So it's not really a price, but it's still a value. So it's called a valuation. Okay. Okay. So now you get the basic idea, this bipartite thing. You got the idea of valuations. How much is each room worth? And you got the idea of perfect matching. Now we go to something, a real thing. Now let's do an example. And this example I'm going to build on it for the rest of the course. This is housing. We have buyers and sellers. The sellers are, I number them with I as the letter and buyer is J. Okay? Each seller, I, has a house. And each buyer wants to buy a house. So for example, you have houses, huh? Here I have 8 little houses. So the sellers are I, 1, 2, 3. And here I have buyers. 1, 2, 3. This is J then. And I have valuations. Okay? So this is V1, 1, V1, 2, V1, 3. So this is for the first buyer. Okay? No, actually, I was going to do this. It's house 2, house 1, 1, 2, 1, 3, 1. So the first thing is the number of the house, and then the number of the buyer. And here we have 1, 2, 2, 2, 3, 2, and so on. So buyer 1, this is the value that buyer 1 puts on that house. And V12 is the value that buyer 2 puts on that house. Okay? So this is the same as the example I showed you before. Okay? This is the same as before. But now we're going to add prices. Okay? The sellers, they don't care who buys. See, the buyers, they care which house they buy. So these valuations will be different. But the seller doesn't care who buys. So he puts the valuation 0 for each house. So the seller doesn't really care. But the buyer cares. Okay? Each seller puts a price on the house. Okay? So there's a price here. Maybe the price here is 100 kilo of euros, and maybe this buyer, for him the house is worth 200,000, okay? So this is the seller is selling this house for P1, okay? And if the buyer buys the house, the buyer has a payoff. So the payoff is the difference Vij minus Pi. That means what the buyer gets in plus. So the buyer thinks the house is worth 200,000. For the buyer it's worth 200,000, but he's only paying 100,000. So the payoff will be V11 minus P1, which is 200,000, minus 100,000 is 100,000, okay? So if the buyer 1 buys house 1, the payoff to buyer 1 would be 100,000. Okay, how much they're getting? They're getting the extra value they're getting. Okay, it's all logical. Huh? The buyer wants to maximize his payoff. So the buyer is thinking between these 3 houses, the one that gives them the most. Okay, so the buyer again is doing like selfish, this rational. It's like game theory. Yeah, the buyer wants to maximize the payoff. If there's a tie, then it doesn't matter. We'll pick one to make it perfect. But if Vij minus Pi is less than 0, then the buyer will not buy, of course. Doesn't want to lose money, and then the payoff will be 0, of course. Huh? So you see how it works, huh? But we're going to do it all with an example. So here's the example. We have 3 sellers, ABC, 3 buyers, X, Y, Z. And these are the valuations for the buyers. So buyer X thinks that A is worth 12, B is worth 4, and C is worth 2. Okay. Buyer Z thinks that A is worth 7, B is 5, and C is 2. Okay. Now the sellers will set their prices. So this is the mechanism. This is the control. So the seller puts a price. Okay. The seller A says, this A, I'm going to sell the house for 500,000 euros. Okay. And B sells their house for 2, and C is giving away their house for nothing. Sometimes you get that, huh? It's an old ruined castle, and C doesn't want to maintain it, sick of it, giving it away. Okay? So what happens? Well, each buyer is going to pick the house that has the highest payoff. So what are the payoffs? So the payoffs, so we can compute the payoffs. So for buyer 1, so there's 3 possible payoffs for A, B, and C. So buyer 1 has valuations 12, 4, 2, and the prices are 5, 2, 0. So the payoff is 7, 2, or 2. So buyer 1 will pick A. Okay? That's simple, huh? Buyer 1 will pick A. Now, buyer 2, so for buyer 2, we have the valuations are 8, 7, 6. Prices are 5, 2, 0. The payoffs will be 3, 5, 6. So buyer 2 is going to pick the third house. Okay, Y will pick C. Okay, and the third one, buyer 3. So the valuations are 7, 5, 2. The prices are the same, 5, 2, 0. This gives me 2, 3, 2. So buyer 3 is going to pick house B. Buyer 3 is going to pick house B. Wow, this is great. Every buyer has a different house. They're all happy. The sellers are happy. They sell all their houses. And the buyers are happy. Each buyer is getting the house with the maximum payoff. Okay? And it works. Why is that? Well, this is, by the way, this is called market clearing. When the buyers and the sellers are exactly matching each other and everybody is happy, the market, it goes empty. It's called market clearing. And it works. How come it's like this? It's because of the prices. So these prices have resolved the contention. So because of these prices, every buyer picks a different house, and they're all happy. The mechanism that makes this work really nicely is these prices. See, the power is really the prices, okay? The prices. So that's nice, right? So this is a good case. But it's not always like that, okay? So I'll use the same example now, but the prices will be a little bit different. Okay, I think it's the same. The prices now are, everything's the same except the sellers put different prices. 2, 1, and 0. Okay? So seller A and B changed their prices. So again, you can figure out what are the best for each house. So X will still pick A, but Y, 8, 7, 6. So the payoffs would be 8 minus 2, 7 minus 1, 6 minus 0, 6, 6, 6. So Y has 3 possibilities. Okay? And Z, well, that's 7 minus 2 is 5, 5 minus 1 is 4, 2 minus 0 is 2, so it's house A with a 5. Okay, now there's no perfect matching here. How can I see that? Well, because both X and Z want house A. So that's a constricted set, huh? X, Z are both wanting A. Okay? The prices now, in this case, they're not market clearing. Oh, it's too bad. The prices are not good. So the sellers will basically, so there will be buyers and sellers who are not happy. Okay? So, for example, whatever house, if Y buys B, then C will sell nothing. Okay? And A will sell to X and Z, so one of those two will be unhappy. So we have unhappy people. Oh, so this is not good. So in fact, what we're going to do in this course, we're going to show how to adjust the price. You can always adjust the prices to make it market clear. So this is the supply equals demand. This is actually a theorem. When you say supply equals demand, people have this intuition. Yeah, the market will automatically regulate itself. But it's actually a theorem. The prices will adjust automatically until there's perfect match, until it's market clearing. So with very simple rules, very simple constraints, it will automatically converge. Okay? So these prices are not good. So in the real world, the prices will change. Okay? So that's the second example. Here's now a third example. This one is, the prices is now 310. Okay, so you can calculate the payoffs and make the graph. I will not do it for you. You can do that. It will be this graph here. Okay. Now, there's actually some ties. Okay, if you look at Y and Z, okay, so Y and Z, okay, so there's actually some problem here, but you can solve it. So Y is going between B and C, okay, and Z is going between A and B, and they are ties. So I have two lines here because it's actually a tie, and X is going to A. So we can actually break the ties to make it market clear. Okay. So if X buys A, then Z is forced to buy B, and Y will then buy C. So if Y and Z, they coordinate, okay, so they buy B and C, then we also can do market clear. Okay. So again, in this case, that we assume that if there's a tie, we choose the right thing, and the prices, again, have solved the problem. Okay? So these are also good prices. So it's only the second example that has bad ones. In this example, there's no market clearing, and so the prices are not good. But here the prices are good. Okay? Okay, so that's an example. So let's discuss a little bit what it means. Okay, so market clearing means supply is equal to demand. Okay, and economic theory assumes that the prices are going to adjust so that you have some kind of convergence. Supply equals demand. Okay, and economic theory says that if buyers and sellers have all the information, and they talk about friction. There's no friction. There's no impediment. I mean, there's really nice communication. There's no problems of the buyer, of the knowledge being transferred. So if this works, economic theory says this is going to converge. Okay? But we're going to show that as a theorem. Okay? So a set of prices is market clearing if the preferred seller graph, so this is the one we just showed, the one where you break the ties, the one where you break ties to do the right thing. If the preferred seller graph has a perfect matching, then you say the prices are market clear. That means they're good prices. They're prices that make everybody happy. Every buyer has a different house. So the prices have perfectly solved all the contention. The prices are the thing, okay? In economics, the prices are really the mechanism, okay? And it really works. Even though everybody thinks that the house of seller A has the most value, somehow they still pick other houses because the price of that house is also very high. Yeah? So even though everybody loves house A, now you notice here, here for example, everybody likes house A the best, okay? Even though it's like that, the prices help solve the problem because they don't value A in the same amount. And A is more expensive, okay? So that the prices actually de-conflict things, okay? So that's the thing. And so that's what I want to show you as a proof, okay? So the prices are kind of, it's sort of like magic. The prices, they move and ta-da, things are market clear, okay? But that's a general property in our formal model. In a bipartite matching market, there exists a set of market clearing prices. So in this kind of example, there's always prices that work. Always. We will never find a case when there's no prices that make everybody happy. Okay, you can always make everybody happy. Okay? And we're going to prove it for the formal model. Remember, the formal model is like idealizing the reality, but still it kind of has the real mechanism of the real world is like in there too. Okay? Also, the prices are socially optimal. That's even better. The buyers will selfishly choose prices. However, the perfect matching has maximum total payoff. Well, that's great. That means it's not just that we have a market clearing, it's also socially optimal. Everybody, the sum of the payoffs is the highest. So the prices is really a nice mechanism, okay? So this is why economics, the usual market economics, why everybody likes it. It makes everybody happy when it's working right, huh? When you don't have people cheating or whatever, but when it's working right, everybody will be happy, and it's socially optimal. That means for the society, it's the best. So actually, it's very nice, okay? The way that usual markets work, the prices, is very nice. So economics is built on this, okay? These two properties is kind of the bedrock, the foundation of economics. So here now you're learning economics, okay? But let me make now a small break, and then I'll show you why it's like that. We'll actually prove it, okay? Okay, on va faire une petite pause. Let me continue now. So we're going to show that markets are working well, okay? That the prices will always converge. We're going to show that. And there's actually these two very nice properties. This is for our formal model. Remember, we have this thing called bipartite matching market, where you have prices and valuations, and the buyers choose the items, and you have a perfect matching. So the real world markets, of course, are more complicated than that, and also because people will not always choose at the same time, and there's more buyers coming and leaving, and it's more complicated. But we're going to keep to this simple model. And the basic notion that the prices converge, this is also good for real world, okay? And the second thing is that these magic prices that make the supply equal demand, the market clearing, they are socially optimal. That means the total payout, the sum, remember what it means socially optimal, huh? The sum of the payoffs of everybody in this game. So this is a game where you have sellers and buyers. The seller strategy is setting the price, and the buyer strategy is picking a house. Okay? and with a certain valuation. And the total payoff, the sum of all the payoffs for sellers and buyers is a maximum. That means if any buyer changes their house they pick, then the payoff will go less. Okay? But we can prove that. The proof is really not hard. It's on one slide, but you have to follow a little bit the reasoning. It works in our formal model. Okay? So the proof is in 3 steps, and it's based on the definitions that I gave. So let me explain it. It's really not that hard if you follow it step by step. Okay? So the first step is, so I want to calculate the total payoff of buyers and sellers. Okay? The first step is that I can show you that that is the same number as the total valuations of the buyers. Remember, the buyers, each buyer has a valuation, 876. So each buyer will pick one of these for the house. Okay? But the buyer will maximize his payoff and not his valuation. Okay? Maximizes the payoff. So it maximizes, so it picks house 2. So here we have a price 5. So the payoff will be, in this case, it will be 7 minus 5. Huh? It's the VIJ minus the price. Okay? So each buyer will maximize the payoff. So I will show you first that the total payoff is the same as the total valuation. And then I will show you that the total valuation is actually maximized. That not just the total payoff, the buyers is actually maximizing the valuation. So therefore, because of number 1, the total payoff of sellers and buyers is maximized. So for number 1, it's basically a property of the formal model. The total payoff of sellers and buyers is the payoff of the buyers plus the payoff of the sellers. Okay? The payoff of the buyers is VIJ minus PI, and the payoff of the sellers is PI, is the price. Now, each house gets bought. Each house that the seller sells, there's a buyer. So each PI in here has a PI over there. So they cancel. Okay? So the total payoff of sellers and buyers is just the sum of the VIJs, which is the sum of the valuation. So, because in fact, the buyers, they get less, but that corresponds to what the sellers get. Huh? So the total payoff of everybody is the same number as the valuation of the buyers. The price of the houses kind of cancels out. And the second point, the total valuation of the buyers is actually maximized. Now we can show that. We have here the total payoff. Actually, what the buyers are really maximizing is the total payoff. Each buyer is maximizing their payoff. But what is the total payoff? Well, the total payoff, again, it's the sum of all these numbers. Okay, VIJ minus the PI. Now we write this sum in a little bit different way. It's the sum of all the VIJs minus the sum of the prices. Here we're not adding in the sellers. We're just looking at the buyers here. Huh? But the sum of all the prices is a constant. Okay? That we assume that the sellers have, these prices are fixed and the buyers are picking the valuations. So the total payoff of the buyers is the total valuation minus this constant. Okay? Each buyer is maximizing its payoff, but since this number is a constant, they're also maximizing their valuation. Okay? I mean, they're picking the house here that maximizes their payoff, but because the sum of all prices all together is a constant, it means they're also maximizing the total valuation. Okay? Because the difference in those two is constant. So that means that the total payoff of sellers and buyers is also maximized. So this is the definition of socially optimal, of course. So the buyers picking, so for given prices, the buyer's strategy is socially optimal. The total payoff is maximized, okay? This holds in our model. It's because of how we define the prices and the valuations, huh? But actually, it kind of holds in the real world too, okay? So this thing, remember then, there's two nice properties. First of all, there exist prices to make it perfect matching. And second of all, these prices are actually giving social optimality. So they're very nice, okay, these existing prices. Okay, now I'm going to show you how the market works. We're going to show you why these market clearing prices always exist. So we're going to try to understand it by kind of making a process that shows you how the market is running, okay? It's a constructive kind of argument. It's showing how the market tries to solve conflicts, and that this is leading, that it's going toward perfect matching, okay? We will show kind of a procedure, or kind of a process, an algorithm that determines seller prices and always gives you market clearing. So it's actually kind of an auction, as you'll see. It's a variation. It's not the same auction as we saw last time. Here we have multiple items, which are the houses, and multiple buyers, and each time the buyers pick a house. So it's like a general kind of auction. So what we're going to do is I'm going to show you a procedure that will gradually increase the prices, and I'll show you that it's moving toward market clear, okay? And always ends up in market clear. So it kind of shows how real markets work. So in the real markets, that's kind of what's going to happen, huh? If there's a problem, if there's many buyers, too many buyers for one house, maybe there's 5 buyers for a house, well, the seller is very happy because the seller is going to increase the price until there's only 1 buyer left. So that's kind of the idea, huh? So the prices will increase until there's perfect matching, until each house only has 1 buyer left. That's basically the idea. Okay? So here it's kind of incremental process, and it will raise the prices according to what I just told you. So initially, all the sellers have price 0, and buyers will choose the preferred sellers. Okay? If there's a perfect matching, we're done. Okay? I just want to show this perfect matching. But usually there won't be. Otherwise, there is a constricted set. There's a set of buyers S that all are interested in a smaller set of houses, NS. The buyers in S, they only want the houses of NS, but there's fewer houses. It's constricted, so the number of houses is less than the number of buyers. We have two houses, and we have 10 buyers, for example. Okay? It's like the sellers are in high demand, and they're very happy. So many buyers are interested in these houses. So what do the sellers do? What would I do if I have many buyers interested in my house? I will increase the price. Okay, that's very intuitive, huh? So in this algorithm, all the sellers here will increase their price. And then we repeat. And we keep going until there's no more conflict. So the prices are gradually increasing, you see? And each time there's a conflict, what that really means is that many buyers are interested in like one seller, but some of them are more interested than others, okay? So if we increase the price, some of them are going to drop out. That's kind of like an auction, huh? It's like ascending price. If you increase the price, then eventually everybody drops out except for 1. Or 2 if they're tied, but tied is okay. Prices will gradually increase, okay? And we will show that it always ends up in market clear. So it always works, okay? So the algorithm is kind of like this. It's doing iterations, which I call rounds. At the start of the round, the iteration, there's a current set of prices. And the smallest one is equal to 0. So we're always somehow arranging for the smallest one to be 0. That's just to make it simple, okay, the algorithm. We construct a graph, preferred seller graph. We check to see if there's perfect matching. If there is, we're done. It's marked clear, and work's over. But maybe not, okay? If not, we find a constricted set, and we know we can do that. There's a theorem, I showed you. Buyers S and neighbors N of S. Okay? And all the sellers in N of S, they are high demand sellers, huh? They have many buyers, so they raise their prices. So the idea is, if you keep raising the prices, the number of buyers will get less and less, okay? Until the constricted set disappears and it's not constricted anymore, okay? And then there's another step here. We always want the smallest price to be 0. It's not really essential. It's kind of normalization. So we subtract the same amount from each price, so that we're always normalizing it so that there's a smallest price is 0. Okay. This is more. This is not really necessary, but it somehow keeps, for the running of the algorithm, it makes things a little bit simpler. Okay. And then it just goes to the next round. So step 6 is not so essential, but you see the idea. We look for perfect matching. If there's one, we're done. If not, we find a constricted set, and all the sellers there raise their price. It's very intuitive, huh? You have to get the intuition, huh? But I'll show you now an example of this. Okay? So here's an example. We have again our 3 buyers and our 3 sellers with their houses. The prices start by 0, 0, 0. Notice in round 1, if it's 0, 0, 0, then every one of these buyers will prefer A. Of course, 12 minus 0, 8 minus 0, 7 minus 0, 12, 8, 7 is the highest. So all 3 prefer A. So A is in high demand. Everybody wants house A. If it costs 0, it's going to have a huge demand. Okay, notice the point of the seller is not to get the maximum price. What you have to get is to find a buyer. If the seller does not have a buyer, then the seller is not happy. In this procedure, the seller will also always get a buyer. But here there's 3 buyers for seller A. So we have a constricted set. S is X, Y, Z, and N of S is A. You see that? You have to understand this. If you don't understand this, then you don't understand anything of what's going on. So you have to understand this, huh? So these 3 buyers all want house A. So what's going to happen in the algorithm? Well, A is going to increase its price by 1. So the price will be 1, 0, 0. Okay. And now again we make the graph, but now the graph is a little bit different. Notice that both Y, in this case, Y will now also like house B. Okay? Because the valuation, it's 8 minus 1 and 7 minus 0, which is 7 and 7. So now there's like less demand for A. Okay? So that's the end of the first round. So now we go to the second round. So the second round, we start, so this was the end of the first round. The prices are 1, 0, 0. Y can now pick house B. So instead of 3 buyers for house A, now we only have 2. You see, the rising the prices reduced it, but we still have a constricted set because both X and Z are still going for house A. X and Z, S is XZ and NS is A. So there's still a constricted set. We still have too much demand for house A. So what's the seller of house A going to do? He's also, again, very happy because he can raise the price again. So now seller A increases the price again to 2. Okay. And now we get another graph. Notice that Y does not like A anymore. The price is too high. You see Y drops out here. Huh? Y does not like A anymore. But now Z likes A, but Z also likes B. Okay. And that's it. But still nobody likes C. Okay. So we're not done yet, huh? We still have a constricted set, huh? So now we start round 3. So you see the prices are slowly going up, and each time you see a constricted set, we do something to get rid of it, huh? So we're like removing the contradictions, bit by bit, okay? So again here, we have a constricted set, because X, Y, and Z are all 3 of them interested in house A and B. Okay, that's the constricted set. It's only with X, Y, and Z. So what happens? Both A and B increase their prices by 1. Because for those 2 houses, there's 3 buyers. So A and B are very happy. They increase the price by 1. And that gives me 310 now. And the new graph. And now actually we have a perfect matching. Okay? We'll see. We go to the next round. Now we're in round 4. We have a perfect matching now. We're done. In round 4, there is a perfect matching. So we basically remove all of the problems one by one when the prices go up. We remove the demand until each house is only 1 person. Perfect matching. The auction ends, and the prices are now market clear. Of course, other market clearing prices are possible. This is the lowest one, but there might be higher ones. Okay, so how do we prove this? Now we're going to prove it. And we're going to prove it using a notion of some number that is changing monotonically. Okay? Some number that basically is always changing, that is always decreasing, and we'll see that it ends to 0. So the auction will only end when it reaches a set of market prices. Otherwise it goes on forever. Right? If we can show the auction ends, then we have market clearing prices. How do we do that? Well, each time we raise the prices, we increase the prices, we remove a constricted set. So we can define something which is like a potential energy. It's a number that is always decreasing, okay? And it kind of corresponds to the, it has some meaning in terms of money. So the buyer potential is the maximum payoff it can get. And the seller potential, it's the payoff, okay? The current price, it's charging, okay? And the potential energy of the auction is the sum of all of them. And so this is why also we want always to have a price equal 0, because we want to show that it's going down to 0. So initially, all sellers have potential 0, and each buyer only will pick its maximum valuation. So there's some number. Okay? So the initial potential energy is some number, integer, which is greater than or equal, but usually it'll be greater than 0. It's the valuation, the sum of the maximum valuation of all the buyers. Now we'll see what happens when the algorithm runs. And we'll see that it sort of goes down all the time. Okay, so here's what happens. So when does the potential energy change? Well, only in 2 parts of the algorithm, at 5 and 6. Let me show you the algorithm again. So here, it only changes when prices change. So here, each seller raises price, here the potential energy is going to change. Okay? And here, this is when we reduce everybody so it becomes 0 again. So this also is a part where maybe something changed. So we have these 2 bits. Okay? So it's basically when the prices are going up. Okay? Okay. Okay, so part 6 is not actually going to have an effect on the potential because we subtract the lowest value, so the lowest price becomes 0. And so each seller is either that or higher number, so it's minus P, and each buyer goes up by P. Okay? So there's no effect. Each seller, each buyer are changing by P. So this is just like normalization. It's not changing anything. The real change is here, step 5. All sellers in NS raise the prices by 1. What does that do to the potential? Okay, all the sellers, so sellers are raising prices. So let me make a formula. So for a buyer, we have this as a payoff. Huh? That's a buyer payoff, Vij minus Pi. And for a seller, this is the payoff, Pi. Yeah? And we know that the number of elements of S is bigger than N of S. That means every buyer, which is in S, and every seller is in NS. So we have the size of S buyers go down, and the size of S sellers, it goes up. So this one goes up, and this goes up, so this number goes down, negative. And since the size of S is bigger than NS, the total potential is going down. Okay? It's going to go strictly down. Okay? At least 1. Because of this. Because it's a constricted set. It's going to go strictly down. And it cannot drop below 0. Okay? So it has to end. So once we remove all of the constricted sets, we have found the solution. Okay? So that shows that we already have a perfect match. Okay? So you have to understand the intuition of this proof. For all proofs, you have to understand why it works. So the reason why it works is that it's an auction. When I have 10 sellers, 10 buyers and 1 seller, if the price goes up, that's a constricted set. If the price goes up, the buyers will drop off because the valuations, the payoffs are not the same, okay? The valuations are not the same. And eventually only 1 buyer is left. Or maybe 2 with equal, but that's not a problem. If they're equal, we just pick 1, okay? So that's the reason why it works, but this is the formal argument. Okay? Okay, so that shows you, this is a basic result from economics. Okay? So we show that supply equals demand is always working. Is that there are always, when you increase the prices, you will find the sweet spot when everybody's happy. Here we proved it for a simple model. We did not prove it for the real world, though. But for the simple model, we proved it. And let me make a connection to auctions. In fact, it's important to see the connections between auction and markets. Because a market is kind of a more complicated auction. Okay? You know, in an auction, usually there's one item and the price goes up until we have one person buying it. Here we have n items, and the prices are going up until n buyers all buy different ones. So you see, it's kind of like an auction too. The prices are going up until the buyers are happy. In an auction, there's only one buyer that's going to be happy, but here, all buyers are happy. So you see, it's kind of an auction, huh? So I want to show you directly what is the connection to auctions. So what we have seen just now is a kind of auction. An auction on bipartite graphs, where we have n items, the price is going up, and n buyers. But in the auctions we saw last week, we had one item and n buyers. We can actually take a single item auction and encode it in this form. This is actually interesting because it shows that you can understand both of them good enough that you can make the connection. So the auction from last week is actually a special case of bipartite. Okay, so assume we have n buyers and a single item. That's like last week, huh? We have to encode it so we have n buyers and n sellers. So how do we do that? Well, we have n buyers. So here's my n buyers. We give each buyer their value, their bid, okay, the valuation, VI, VJ, like for the bidding. But we need to have n sellers. So we add some fake sellers here, n minus 1, so that we have a total of n. Okay. And the buyers will have valuations 0 for these fake sellers, for the other ones. Okay. And now you can see, if you run the algorithm, it's going to do exactly like the auction. An auction from last week. It's an ascending bid auction. Okay? So for example, the prices are going up. So the price raising procedure that we saw, it's actually like raising prices in a single item auction. So initially, all buyers are going to A. So the S is the set of all buyers, and n of s is just A. So this is like all the bidders are going for that thing. But as the price goes up, the bidders will drop away, will drop off. Okay? So the seller raises the price by 1 unit. Okay? It keeps going. Okay? The real seller will raise the price. For example, here, it's raised 2 items. So this continues as long as at least 2 buyers have the real seller as the unique preferred seller. Finally, we only have 1 buyer who prefers the real seller. Okay, so we're going to do kind of a second. Price auction. So here we have 2 and 3, okay, and buyer, and so it's like a tie. No, it's 3 minus 2 is 1. In this case, buyer X. So let's see what the valuations are. So it will not pick. It's only 1, so it will not pick A, and it's either 0, 0. So it's B and C. Y will pick A, and Z will pick 0, 0, 0, either A, B, or C. So here Y wins. Okay? Okay? So at some point we only have 1 buyer who prefers the real seller. This happens. Remember, the prices are going up by 1 unit at a time, just very slowly. At some point, the buyer with the second highest valuation drops out. At that point, the buyer with the highest valuation will pick the price. The price will be the price of the second one. Okay? Because it's exactly at the time when this guy drops out. So this is like how an ascending bid auction works. So it goes up slowly. What I like to call the James Bond auctions. The prices are going up slowly, and at some point, the second guy drops out, and the first guy wins. But at that point, the first guy pays what the second guy has, with a small difference, with epsilon difference. So this is exactly an ascending bid English second price auction. Okay, so you can see there's actually a strong connection between market supply and demand and second price auctions. It's funny, huh? You might not think that these two things are connected, huh? So second price auction and markets where the prices are going up until we have supply equals demand, that's actually just a generalization of second price. So you see, second price is even more important than it's done not just for auctions. The whole economy works on second price, actually. Yeah? It's the same mechanism. Huh? Okay? So think about it. It's actually the same mechanism. Huh? Okay? Okay. Okay, so let me summarize what we saw now. So markets, it's basically, you have many participants interacting instead of just N and one seller. And prices are the thing, huh? The one word in today's course, important, is price. Right? The prices are a decentralized coordination mechanism. So what we did, we studied in the idealized market. So we defined this bipartite matching market. And market clearing happens when all buyers are connected to different sellers. Everybody's happy, basically. Yeah? So this is a perfect matching in our model. And in our model, again, we show that you can always find prices to do market clearing. So this is all idealized. Huh? So the proof I gave you of this, it works in our idealized market. So in the real world, things are not so simple. Huh? But in the idealized model, it's actually generalizing the ascending bid auction. So it's similar to the second price auction. Huh? So it's actually kind of an auction. So markets are like auctions. So auctions and markets are very close together. Huh? You can see, huh? They're not totally different things. They're very close together. So in a real world market, what does it mean? Okay, it means in real world, you have this notion supply equals demand. But what happens in a real world market is that everything is always changing. It's very dynamic. And prices are always changing, but they're always converging. So the idea is, if a seller has many buyers, the seller will increase the price. If the seller has no buyers, the seller will decrease the price. Okay? But usually there's many items. The seller is not just selling one item, but many replicas of the item, like cars or televisions or whatever. So it's not just one item, but still there's n items for each seller. But still, the same idea is holding. If the number of buyers is bigger than my production capacity, then I will increase the price. If it's less, then I will decrease the price. So you're always converging, okay? So this notion of converging is generalizing the ascending bid, where the prices are going up. In real-world markets, the prices can also go down a little bit. Huh? Okay, so that's all for markets. Okay, we're actually a little bit early, but that's not a problem. I think I will stop here. So think about it carefully, do some of the exercises, figure out how it works. Also understand how auctions and markets are like very close. They're not totally different things. Okay, so try to get intuition on that. But also the formula. Okay, donc je vais mettre là.